and well it's designed or set up, that single point it's not that very often. You don't encounter that very often. Okay. And with this, information flows have a higher guarantee of reliability, or unlike this one over here, which you could have a number of uh, some challenges that could happen over here in terms of overusage of bandwidth or overusage of channels and what have you. Information flow can, if it's not properly implemented, can have issues. By the channel, if they're well implemented, it's actually a huge advantage. The internet uh, uses a more or less a mesh-like topology because you have devices that interconnect from different points with multiple points just so that be able to handle redundancies and address single point of failures or whatever. So the internet would be a typical example of what a mesh topology would have. Whereas your more or less basic individual or institutional organizational network implementation will fall within this in the star topology. We also do have bars and ring. Bars is usually when the device share a given medium, and there's so many issues with this. That's why one of the reasons why today it's not advisable. Most systems don't even use this type of topology anymore. The only system that probably uses this, most of the computer uh, devices for handling memory and memory allocations, storing of information, putting of various operating systems, and handling other system executions. Is where you'd probably find this kind of implementation. But at a network level, it's quite rare to have a ring topology. Okay, so at a network level, you're not going to find these. These are more obsolete. They're quite gone out of the system. I'd be surprised if I came across a network system that uses a bus topology. With this, I think one of the biggest issue with this the bus topology is that it has a single point of failure, which is just you have one medium that you're working with, and with this one medium, in case uh, there's the, the medium here gets cut off or gets severed off, then it basically affects the information flow from this point to the rest of the other devices. You get a picture? So if there was supposed to be a breakage or interruption within any of these uh, mediums in between the various devices, then information flow to other devices on other ends of that bus topology becomes a huge problem. The other one is a ring topology, which is today being used a lot by most fiber optic networks. Yes, fiber optic networks use that a lot, and it's been quite reliable in terms of how the information flows. It does have some of its downside, but implementation is a key thing to addressing the downsides. The good thing is that a properly well implemented ring topology would have multiple rings uh, to avoid single point of failures. Okay, would have multiple rings. So each device will probably have a different another ring attached besides one or two rings to you to address any kind of disruption that might come up from a given uh, uh, issue or challenge within the implementation, so as to avoid single point of failures within the network itself. You don't really see uh, what you call it uh, copper networks using or copper mediums of transmission or copper mediums of transmission using ring topology. It's mostly, from what I've observed over the years, it's mostly fiber optics, just to give that hands off to all the various devices within a given network. Now, this diagram, keep in mind, is just the PCs that you see are just representing network devices. That's what they are representing. Okay, so it doesn't necessarily mean they are PCs. Obviously, they could represent mainframe servers, other high-end network equipments, then various setups. But the most important thing is they more or less within a ring format where they interconnect to various other devices to allow the information flow to be possible in kind of like a ring circle, a ring form. Okay, hence the word ring topology. Okay, so those are the four one of the four major topologies that we have today. They are the hybrids. There's a hybrid which incorporates a number of the mesh and star topology together, as well as something the ring. Or and it is employed within uh, various implementations as well. But generally, these are the four main ones that you probably would kind of like encounter yourself with or be come across within various network implementations today. Although these two are more or less the most widely used today, you do, like I said, the four main ones that we need to just keep in mind. Okay, so that's what you need to look at. And like I mentioned earlier, there's the hybrid forms that adapt some of these topologies. Um, um, yeah, in a way, so a hybrid will consist of practically all the four in a way. Uh, either either this mesh star or ring, or it could be star, ring, and bus, or it could just be purely just star and then bus put together. So that's why it's hybrid. You can mismatch some of these to give you that particular service that you need. So exactly, you do have the hybrid topologies where star backbone is implemented. So you have a star backbone, and then the bus is actually used to integrate it with. So yeah, so they have, in this case they have a star and then a bus being combined. It could be in another form of hybrid could be a mesh mixed up with a ring, or a mesh mixed up with a star, whatever. Okay. Hierarchical organizations of internet. So after we talk about the topologies, we'll look at the hierarchical organization of how the internet is structured, and this way we'll look at various levels within internet service provision. So we do have at the top level, you have your ISPs. Your ISPs provide your internet service providers. They provide services to regional ISPs. Usually, your ISPs at the top layer are more or less uh, the the content providers, like the Googles, the Yahoos, and uh, uh, more of the big guys at the high end, mostly ISPs that actually owns more or less the core uh, transmission mediums. Okay, and Google has a huge chunk of that. There's Orange from the US from the European region. and other kind of number of them. So those, and that's one of the big content service providers also do have do form part of the top hierarchies, and they usually provide services to regional ISPs. So regional ISPs in this sense would probably be uh, probably use companies like Main One, Glow, um, Watt, Sats 1 and 2, and 3 as well. Those are some of the key. I'm looking within our region. Those are the guys who consider the regional ISPs. They take their transmission from the highest hierarchical order of the ISP levels, from the big, giant uh, internet service providers, and they also have a way of basically um, reselling that their service to your national ISP. So your national in this sense will probably be your Vodafones, your MTNs, your Tigos, your Airtels, and what have you. So they would be at this more or less level of the hierarchy. So you have a three-tier hierarchies where the big guns, the big ISPs are the more of this the key internet infrastructure owners falls under, and then they supply services to regional ISPs, and then the regional ISPs redistribute that particular service that they've gotten from uh, uh, the big ISPs to the national ISPs. Okay, and then the national ISPs uh, go deals directly with the individual subscribers within a given country or region or locality. Okay. Yeah. Oh. So anyway, so this is how you have the interconnectivity of national ISPs. So you do have a number of national ISPs. So this is like saying MTN connecting to maybe Vodafone, um, and um, and one of them happens to be connected to the NAP, which is uh, your national what is a NAP, by the way? It's national something. Premise is national access premise. I think it's national access premise. Sorry, the network access premise. Okay. So this is where key network devices interconnect to. Key network service providers at the national level interconnects to, and then you have other national service national ISPs interconnect to also resell their service to other service providers within a national ISP region. Okay, so you have your network access points and various big national ISPs would connect to. That's what's going about with the service with some of our ISPs. You can say maybe probably use yes. Let's use Vodafone here or MTN here, provide a service to maybe Teledata or maybe providing a service to Comsys, you know, but they're all essentially interconnected at the network access point or the network access premise. So that's where you do have all of them interconnected too, as the central point of information communication or information interconnectivity. So now let's look at layering stacks. Layering stacks here, we're looking at how the various protocols that allows for the information or for the data communication to flow uh, seamlessly based on particular standard sets or based on particular rules put together or that in various uh, uh, designs that have been well structured for information flow to take place. So we're going to be looking at some of the protocols that makes up some of those layering stacks that makes the information flow within various network devices possible, either from the computer through a network, which is through routers, switches, and and back and forth, between a sender and a receiver. Okay, so that's where the layering stacks and the protocol stacks comes to play. So that's what we're going to look at right now. I want to look at some of the layering and protocol stacks. When it comes to protocols, we want to kind of define what it is between humans and computer systems or network systems. When protocol is mentioned and the human point of view, we're looking at, let's say, for example, what time is it? If there's going to be an event, the question is what time and day is the event coming on? That's one of the protocols, or within a conversation, you can say, I have a question, you know, and then obviously you introduce when it comes to first time meetings, there's an introduction, okay, and then specific message are exchanged or sent back and forth, or specific actions are also taken uh, from the various events or from the various gatherings that you might have. But when it comes to network protocols, they are more related to devices, machines, or computer systems. So that's what we talk about how machines, rather than humans, uh, communicate activities over the internet under a governed rules, okay, or under a governed law or structured form or standard, okay. So there you go. So you have the human part, time, questions, introduction, specific messages needs to be sent, and actions also needs to be taken from all of these events or gatherings. Whereas when it comes to network, it's more machines and how communication activities within the networks are well governed to make information flow possible based on protocols. Okay, so a protocol we define as format, order, or message sent and received among network entities and actions taken on message transmission, either via recipients or a sending node. So within humans is hi, reply hi, what time is it? Tell me time. Computers, on the other hand, will use protocols like transmission control protocols, which is TCPs. It's highly required for two devices to transmit information, as well as have information to reply back. So both falls within a huge TCP TCP connectivity requirement. And once there's that agreement in terms of how the transmission control protocol is managed, then information flow takes place. Okay, and then standards are essentially uh, they're quite essential in creating and maintaining an open and competitive market for equipment manufacturers. So we're looking at how devices, what kind of standards devices needs to meet in order to make provision for interoperability between other devices as well. Because obviously we know there are going to be a number of manufacturers. Computer systems or network systems are manufactured by a number of companies, a number of organizations. The question is, do they do their own thing? Obviously not. If they really want to partake within a network transmission, there has to be some kind of standards that they must all follow. So there has to be a basic fundamental standard that they all need to follow, and that's where standard comes into play. So it's essentially in creating and maintaining an open and competitive market for equipment manufacturers to be able to meet a given standard that cut across all those device designed by them, and also guaranteeing national and international interoperability of data and communication technology as well as its processes. Okay, so layering stacks, for example, when it comes to humans, we look at like for instance, when it comes to mail delivery by the post office to the post office system. You'd have you write a letter, you put it together, put an envelope, put an address on it, go to the mailbox, drop it in there. The mailman comes, picks it up, and uh, transmit it. To look by looking at the address on the mail on the envelopes, and then finds a way to route that message either via courier service or what have you as a medium to a destination recipient. So that would be the layering stacks for human day-to-day activities. When it comes to post office as an example, but when it comes to this like a parcel delivery, from a human point of view, or when it comes to uh, computer systems, obviously there's going to be a difference here, you know. Uh, but we do need that. But generally, the reason for having that layering stack for communication is to reduce complexity of communication tasks by splitting into several layers for small tasks to be possible to handle, as well as functionalities of the layers, which needs to be changed as long as the service provided to the layer above stays unchanged. Okay, so making it easier maintenance and upgrading as well. And each layer has its own task that needs to perform. Okay, it has its own task, and a task also follows its own protocol. So it's as long as you have specific um, layers for a given service that needs to be rendered, system have got ways of handling some of these things within their own respective assigned tasks. So there are key things that systems generally observe within their information flow. Okay, and most of them, like I said, they are well, like pointed out earlier and not long ago, is that each layer that a particular service falls within, or that an information task is split into, has got a specific task or a specific job that it needs to undertake. And then there's also the protocol aspect of it. Okay, and so they're all unique in their own way. So we'll look at some of these layering stacks. This is where your OSI models come into play. So looking at the various roles they play at or various rules that are observed at a given layering stacks within the open interconnected system. Um, yes, the open system interconnection models, which is the OSI models. Okay, so that's what we look at. When we look at some of these layering stacks, which relates to the standard. So generally, I guess you could say that what's going on is the whole concept behind having layered communication, which obviously is to reduce complexity and what have you, as well as functionality, uh, is to hand off respective tasks and protocols to each and every layer. So that the information flow doesn't get staggered up to just one layer or one particular section to handle. Okay, and so that's where uh, the uh, Institute of Telecommunication Unit has come up with a standard, which they call the OSI, or the Open System Interconnections rule or model, to help make sure that the tasks that are assigned to specific layers are well defined and well addressed when it comes to that particular layer. So we do have the open system interconnections reference model. And we also do have the TCP/IP. So there are two main models when it comes to network um, data communications. Okay, we do have especially when we talk about the layering stacks involved or the roles of layering stacks in communication. There are two main models that have been designed. There is the Open System Interconnection reference model or model, and then there is the TCP/IP, which is the Transmission Control Protocol / Internet Protocol model as well. Okay, so we'll look at this very quickly. There are generally 7 layers, okay, and they do create layers when different abstractions is needed. Each layer forms or performs a well-defined function, like I said, we pointed out earlier on with the responsibility-wise, and functions of the layers chosen um, usually taking internationally standards protocols into considerations. It's one of the things that the layering stacks also looks at in terms of within the model. Okay, so the model is essentially created to help with the functions of the layers, choosing to take international standard protocols that are involved, and then the number of layers, which is large enough to accommodate complexity. Okay, so there are 7 OSI models. Okay, and I was just briefly talking about some of them and how the role they play within the model. So creating a layer when different abstraction is needed. Each layer performs specific and well-defined task or function. Functions of the layers chosen take internationally standard organizations into consideration for their protocol implementations. And then obviously the numbers has to be large enough to afford complexity within the implementation. So at least we can manage uh, issues that could relate from jitters, delays, latencies, throughput, and what have you. Okay. So here are the 7 layers. The highest one usually starts from the bottom to the top. At the topmost, it's application layer, and with a presentation layer follow up, and then the session, transport, network, data link, and physical. So that's how the information flow goes from a sender to a receiver. So you can notice just that way around. Usually at the bottom layers, at the physical layer, it's more or less bits and bytes being transmitted within a medium, which is actually going to be translated either signals using various encoding techniques to move it through the medium from the source to destination. And when it reaches the destination, it just goes in reverse order. So if it's at a physical medium or physical layer, then when it hits the first layer, then it gets reassembled as bits and bytes, and from bits and bytes at the physical layer, it gets regrouped again into uh, the data link layer, where the information gets shrunk a bit to the specific uh, encapsulations for frames and what have you. Okay, and then from there it gets moved up to the protocol, so to network layer where you have packets being addressed. Okay, and transports and sessions presentation. Finally, the application layer all over again, but the message gets handed over to the recipient from what it was actually, what it actually looked at from the sender's point. So in a way, we're looking at just how the information is broken down from the human view all the way through the computer's layering stacks view to go through medium, airwave, or either wired or wirelessly, and then the reverse procedure takes effect to regroup the information back to what the actual information is at the receiving end. So here's more of some examples. So this is where routers and switches and what have you plays a key role in addressing some of these issues or in terms of managing that flow of information from the application level all the way up to the physical layer, the first layer, layer one. Okay, so bigger issues comes up when you start considering a number of these issues or a number of these implementations, and some of them are larger bandwidth at lower cost, error corrections, flow control, address and complexity, naming, condition controls, mobility, routing, fragmentation, security, blah blah blah, what have you. Okay. So that's some of the issues that needs to be what resolved by the layers. Larger bandwidth at a lower cost, managing error injections, flow controls, making sure you have the right IP address for the transmission to be passable from a sender to a source, or from a source to a destination, or from a sender to recipient, and multiplexing and how the information is grouped together within various transmission points. Then you have naming, congestion control, mobility, and routing for storing and forwarding information, various algorithm and protocols that needs to be implemented to make the that levels, tasks or roles or responsibilities or protocols performed properly, and obviously fragmented information and security as well. So the OSI layers in depth, look at some of them, break them down. The physical layer is more or less transportation of bits from one end node to the next. So we look when it comes to the physical, which is layer one, it's more or less about how your bits are transmitted. Okay, from one node to another node. Now, types of transmission mediators are used at the physical layer revolves around twisted pair, coaxial, fiber optics, and then obviously the airwave or your wireless, your radio wave. Bit representations are based off voltage levels of logic values, like within the signal encoding, as I mentioned, within that, your bits are more or less going to be interpreted using various voltage pulses. So voltage levels either at the high level or at the low level or the negative level, depending on the encoding technique being used. So that's where bits representations take effect or takes place. And then you do the data rate, which is usually the speed, as well as the synchronization of the bit, which is the time that the information actually form after it's been spread out or taken through various medium. At the receiving end, it needs to be put back together. So that's where the synchronization comes into place. So all of that is addressed under the physical layer. So generally, in summary, you can say the physical layer is responsible for the movement of individual bits from one hop to the next. Okay. And then the data link layer, we have transportation from frames or frames, so transportation of frames, uh, from one end to the next. So here we're looking at how switches more or less relay information. Okay, and that's how usually frames. Switches carry frames, whereas the analytic layer will carry packets. So at the physical layer, we carry bits, and then when exiting a medium level, it's more signals. But from the physical layer, when we moving on up to the data link, we're talking about frames. It's more encapsulated into frames, and the network is more the packets. Okay, so framing and flow controls, access control, physical addresses, which is where your MAC addresses play a key role, and error controls are key um, requirements that needs to make the physical layer handle the task efficiently, effectively. Okay. So here we have examples of how um, the data link layer handles information flow, within a given system. So in this case, we operate just within the last two layers. Yeah, the last two layers of the OSI model. So you have a device here, an end system, send information to either one of these devices here. In this case, it's A to D and F. And then we have the mediums that are more or less playing a role in information transmission. And analytic devices that makes it possible for the information being carried back and forth. So you have a router, so you have a PCO, a computer, or network system that's connected to through a link, wired link over here, to a router, and within the transmission information from the data link are more or less within frames, and then handed off as bits when it counts its transmission over the medium or the link. And then once it gets to the router, it goes up to the highest point of that particular level of layering style that we're considering. So in this case, the data link. So if we were setting frames, that's how probably would go about. And then if the source of the destination is not around here or it's on a different particular point of information, then it's the job of the router to know how to handle that frame coming through and then handing it off to the required destination link or transmission if possible. So anyways, so that's how the information flows, especially within the first two layers. Okay. So if you notice at each and every routing point or node point, the information has to go through the first two layers until it gets to the final destination node or recipient or the end system. So another example, this is for the hub-to-hub deliveries, and this one is more or less on giving switching level um, from one device to another on one given device or network centralized system. So information flow handles message from this end device onto this, usually based off the physical address, which is the MAC address. It's where um, the main destination address is looked at from, so it can make the information for the data flow possible. So there's a trailing bit, there's the information itself, and then there's the source address and then the destination address. So to summarize a data link, we can say the data link layer is responsible for moving frames from one hop to the next. Okay, so that's your summary of the data link, which is a layer 2, being responsible for moving frames from one hop, which is a node, to the next. Okay. So from that, we'll basically halt and then continue the rest of the layering stacks on the next lecture. Um, the material that you're supposed to be reading should come from Data Communication and Networking Textbook by William Stalin, and the contents page for this particular layering stacks can be found at chapter 2 from section 2 all the way up to 1 to 5. Oh, sorry, from chapter 2, section 2.1 to 2.5. That should handle most of the layering stacks and protocol stacks that we have within the data communication uh, introductory and fundamental points of view. So we'll continue on the subsequent layers in the next lecture. So